Hello everyone, and nice to see you again. This is my second video, and yeah, yesterday was a good start, a warm up, and after yesterday, I thought like I want to you know, explain some problems or like uh teach some problems on these videos because I'm also an applicant this year, so uh I think maybe the best way for me to practice is uh do it on the videos. So uh, from now on, my I will do solve the problems directly on the videos, and you can pause and try to think it by yourself. Okay, yeah. So today my topic is doping equations because I think doping equations is a very valuable thing in interview. Doping equations needs to uh using a lot testing the ability from the number theory and inequality and stuff like that. So yeah, so because interviewer wants to test all your mathematical skills in a very short question, in very few questions. So I think like doping equation is a good way to train. So yeah, so I picked several problems here, and yeah, okay. So mm, the first is find all x, y, which are positive integers, such that x squared plus 3y, y squared plus 3x are all perfect squares. Okay. Okay. So now this is a totally new question for me, and I need to solve it. I need to solve it on this video, and to yeah. So to the you can pause it and try to think it of by yourself and check whether like we are of the same. Yeah, so check whether we are doing the same thing. Yeah. Okay. So now x squared plus 3y, y squared plus 3x are all perfect squares. So yeah, so firstly, 1 is a trivial solution here, so and it doesn't matter. So it's quite trivial. And uh now we are testing some properties of perfect squares. So yep, x squared plus 3y, y squared plus 3x. Okay, so to this doping equation, I may try to use the inequality because as because like one consider the perfect square numbers 1, 4, 9, 16. The difference of it is increasing, and x squared plus 3y is larger or equal than x plus 1 squared, of course, because if this is square number and equal to this cannot equal to x squared, so it had at least be x plus 1 squared, and this is yeah, this shows still this is larger or equal than y plus 1 squared. So by the difference of um, square numbers, which is 3y larger or equal than 2x plus 1, and 3x is larger or equal than 2y plus 1. So by this means, we can obtain like y is larger or equal than 2 over 3x plus 1 over 3, right? And if I put this here, if y is larger or equal than 3, so like 3x is larger or equal than uh 4 over 3y plus 5 over 3 to y. Yeah, but sorry. But this, I think this cannot tell anything about it because uh to me I want to find an upper bound. Uh yeah, I want to find an upper bound solution. So I think I may try. So if I let x squared plus 3y, if I let x plus 1 squared be available for it, first I may check whether this will happen. 2x plus. Okay, so this so means that 3y is larger or equal than 2 times x 2 2x plus 2. Okay, so 3x is larger or equal than this. So 3y is larger or equal than 4x plus 4. So y is larger. Yep. And so firstly, because if I just consider like the difference between this is x plus 1 squared, this is y plus 1 squared, I find that it's too weak. So I may change another method to yeah. So yeah. So I think I may try to prove so try to release x plus 1 and y plus 1 and try to prove that uh, in the form of inequality, right? So yeah, I think I get this because uh so if both of so if the both like if I let it be a squared, I let it be b squared. If a and b are both different from x or y over 2. So like if a is equals to x plus 2, b equals to y plus 2, so this may x squared plus 3y equals to a squared, or yeah, x plus a squared and x plus squared plus 3y squared plus 3x equals to y plus b squared. Let it here. So firstly, if a larger than 2, b larger than 2, so which means that x squared plus 3y squared is larger or equal than x plus 2 squared, and y squared plus 3x larger or equal than y plus 2 squared. So by the meaning of the difference of perfect squares, 3y is larger or equal than 2x plus 2. So 3y is larger or equal than 4x plus 4, and y larger or equal than 4 over 3x plus 4 over 3. So which indicates like y is larger than x, of course, right? Yeah, and by the same mean, we can obtain like x is larger than y. So this contradicts, right? So yeah, so this is a good approach. We reduce the range, and the only possible cases is like uh x squared plus 3y equals to x plus 1 squared. Uh, x y squared plus 3x equals to xy plus 1 squared. This is the first case. And the second case is something like one of it, I just let it be x, so it is x squared plus 3y equals to x squared, x plus 2 squared, and y squared plus 3x equals to y plus 1 squared. And the third case is both equals to x plus 2 squared. So if both takes the equal sign, which satisfies it. So it cannot be true, and only these two are possible. And so first, let's consider the first case. Okay, so both a and b equals to 1. Okay, x squared plus 3y equals to x plus 1 squared. 3y equals to 2x plus 1, and 3x equals to 2y plus 1. So this is yeah, a function with two variables, and of equation with two variables. And if so I think this I times 3 on both sides, which means like 2y, sorry, 9y plus equals to 6x plus 3, and 6x equals to 4y plus 1. Okay, so 9y plus 6x equals to 6x plus 4y plus 4, right? Plus 5. So 5y equals to 5, and y equals to 1, and x equals to 1. This is my first trivial solution. So it's 1 and 1. Okay, and then let's move on to the second case, which is x squared plus 3y equals to x plus 2 squared, and x squared plus y squared plus 3x equals to y plus 1 squared. Yeah, this is the only case here. So 3y equals to 4x plus 4, because like by the means of differentiate the difference of the square numbers, 2 times 2x plus 2. Okay, and x equals, so 3x equals to 2x plus 1. Okay, and x equals to 2y plus 1. So yeah, of course. So it's just I just need to solve it. 3x equals to 4x plus 4. So 6y equals to 8x plus 8, and 9x equals to 6y plus 3. Yeah, and if I add them together, what still by the same means, 1 plus 2 equals 2. So it's 9x plus 6y equals to 8x plus 11, right? So x equals to 11, and y equals to 16. Yeah. So this is the other case. So the only two cases is 1, 1, 11, 16, and 16, 11. Of course, if it's counted. Yeah. Okay. So this is my first question. It's a little bit hard, but I think like take a review from this question. Take a review from this question. Firstly, I take approach to sorry, it's quite hard to change the pages. It's also this is what the Tencent meeting is like a shit. Yeah. Okay. So this recording is hard to yeah, it's fucking okay. So let me take a review. So firstly, I get if I if these two must satisfy, like these two are all perfect square numbers, I found like I would firstly would like to use the inequality solve to solve that because yeah, so I think to me when I'm facing the problems about perfect square, the first thing I think is to find some properties of perfect square, like the last digit or the modulus to 4 towards 4, right? But because x squared plus 3y, y squared plus 3x. So I think it's quite it's a quite strange because like this is are a symmetric kind of. So I uh, I adapt the inequality, and firstly I made a better approach, and uh, then I released the x plus 1 case out and just focus on both are larger or equal than 2. And yeah, and I found this works out successfully quite well. So I think this is a little bit hard. And the other Diophantine equation I picked, I think is I think it's harder. Yes. So find all x. It's hard to yeah. This z is at first I always use this z, and my friends told me that if I use this z in the interview, this may the professor may didn't know what may don't know what I mean. So I yes. So I learned to I learned to use this z sign here. Sorry, oh, sorry, caught the fever, caught the cold. Okay, so this is another doping equation I picked, and uh, I didn't know how to do that at first. So by observing, I think like it's a very strange um, equation because the left hand side is a series about factorial and right hand side is uh yeah, so the right hand side is power, it's a form in power. So these two are a totally different, right? So one one factorial plus two factorial. Okay, so firstly I'm trying to find some properties on both sides. So what about the parity of this? I think parity is the first thing I may need to take into account. So only this is an odd number is 1, and after 2 factorial, odd numbers are even numbers, right? So so firstly, left hand side is odd number. So y is odd number because if y is an even number, so y to the power of z, of course, it should be even. So yeah, left hand side is an odd number. Okay, x larger than 1, y is larger than 1, z is larger than 1. So y to the power of z. Okay, so let's try to discover some more properties. Y is an odd number, and uh, consider the yes. So let's consider model of 3. 1 factorial plus 2 factorial equals 3, and all the numbers after 3 factorial are factors of 3. So firstly, left hand side is a multiple of 3. Ah, so y is a multiple of 3, of course. Okay, so yeah, 6 factorial. Y is odd. Y is a multiple of 3. So what's next? Y to the power of z. So the right hand side, if y is a multiple of 3 and z is larger or equal than 1, so we can, like, right hand side is at least a multiple of 9, right? And let's consider the modulus of 9 on the left hand side. So after 6 factorial, of course, odd numbers are multiples of 9, right? Sorry. So consider 1, 1 plus this plus plus 4 factorial, which is 4. 4 factorial, which is 24. 5 factorial, which is 120. So this is 3, this is 30, which is congruent to 6 modulus 9. And yeah, this is congruent to 3 modulus 9. So, and yeah, so firstly, if x is larger or equal than 6, left hand side, so 9 is divided by x left hand side, right? And yeah, when x is equals to 2, maybe sorry, when x equals to 3, there's also, and first let's deal with the case when x equals to 3. So x equals to 3 is the uh, only case with x smaller than 6 that left hand side is divisible by 9, right? So this is 1 squared 1 plus 2 plus 6, which is 9, and this equals to 3 to the power of 2. Okay, so there's, there's our first there's our first case, which is x equals to 3, y equals to 3, z equals to 2. Okay. Okay, and let's still consider this question. So after this, x should be larger or equal than 6 here. Right. Uh, x is larger or equal than 6, and so what's going on? There's one approach which is like consider like z is 2 or z equals to z is larger than 2, and because z is larger than 2, left hand side should be a multiple of 27. And wait, let me check. As x is larger than 6. Yeah, but 27 is quite large, I think, because uh So what about just put it away? Just uh just x is larger or equal than 6, and this equals to y to the power of 3. Y is multiple of 3. And uh okay. So uh so I may need some hint, and the hint is from the book. Okay. So the next step of the book is just like what I said before. It is very, very terrible, I think. So checking the uh, models from 27 is very fucking. And now, yeah. So after checking, so like this is from I equals to 1 to 8, I factorial equals to this, and it's not a multiple of. Okay, so this is told by book. Okay, so this is a small hint by book, and I will move on. So now, because z cannot be larger or equal than 3, so z can only be 2, right? And this will become better, I think. And uh, 1 plus 2 plus 3 plus 4. So this is a square number, and like I said before, I may try to use some properties of it because now this is nothing about inequality as the previous question. So firstly, let's check the last digit to check whether it can be a square number. Yes, so it's 1 plus 3 plus 6 and plus 4. So it's 3 plus uh 1 plus 2 plus 6 plus 4, and then plus all 0 plus 0. So this with last digit 3. And uh, okay, because when x is larger or equal than 5, all are 0, because there's a 10 here, and just consider the previous 4 digits. And when x is larger than 3, the last digit of this is 3. And I think like now I'm introducing a quite a useful method to check whether it's a square number, which is check the last digit. So 1 squared with last digit 1, 2 squared with last digit 4, last digit 9, 4 squared with last digit 6, 5 with last digit 5, 6 with last digit 6, 7 with last digit 9, and 8 squared, or like um just consider the last digit of it. Okay, 8 some something 8 squared is last digit 4, last digit 1. So 3 is not on the list because uh yeah, so I may try to prove it more clearly. Because like yeah, so because the last digit is just determined by the last digit of its square root, right? So 3 is not at least. So if x is larger or equal than 2, it cannot be a square number. So there's no solution. Okay, so the only case is 3, 3, 2. Yeah. And the question is done. And yeah, so let's take a small review by this question from this question. Uh, yeah, I think I did it well. I think I did it well. And um, in this question, I first test the parity. I first test the uh, modulus to 3, and these things are I think are very, very common in doping equations. So yeah, this, and then after I tested these both I try to find that because of z, because z because left hand side is not a multiple of 27, and I don't think like this is a very good attempt here because it involves a 5-digit number. I cannot calculate it out, and I didn't know that whether it's a multiple of 27. I did this is from the hint. This is the hint from my book, but in general, this is kind of good question. Good question, and I think like uh to review from this question, this is something I can teach taught me, which is like consider if there is a power on the doping equation, so try to consider of the prime factors, the power of the prime factors. Now, I think I did it greatly. I considered the 3 power of 2, the 3 power of 3, and yeah, because this is very uh, useful property of the power. Okay, so this is my Cambridge interview 2, and if you like this, please subscribe. Or this is subscribe. Okay, yeah, it's okay. But if you are also an applicant this year, you can contact me and we can book some interviews online, both picking some good questions and ask each other. Okay, bye bye.